Good morning. Okay. Good morning. I'll start with a quick recap of what we did last time. If there are any questions, you could stop me at any time, including now. I will kind of quickly go through what the main points of the last lesson, and then continue from there. So basically, our starting point was Newton's second law. Again, you have it written down, so you don't have to necessarily copy what I'm writing now. Newton's second law, which as always is x double dot equals F over m. But we did that for an ideal spring. An ideal spring means that F equals minus kx. If we write it not as a vector, this, for some reason the recording here. Yeah, okay. So if we write that together, we have x double dot equals minus k over m multiplied by x. This is a differential equation, meaning that we have the second derivative with time on the left-hand side of x, and then we have x itself on the right-hand side, which is a nuisance, so we have to guess solutions rather than solving it. But the guess solution that I showed you, which works, or one guess solution which works, was this one, which was the complex exponent. So it's a multiplied by a complex exponent, so it's e to the power of I square root k over mt. And we spent some time, I hope convincing you, that when you differentiate this thing twice, it actually obeys that equation, okay? And we also talked about that a complex exponent is simply a way of writing cosines and sines together, or more specifically, means that this x can be written as a multiplied by cosine square root k of m times t plus some imaginary, so plus I square root of minus 1 multiplied by the imaginary part, which is a multiplied by sine, again of the same thing, square root k of m multiplied by t. So this is the real part, and this here is the imaginary part of the solution. Now, what we said, what I said, and you guys kind of agreed, or at least were quiet, was that each one of the halves of this x, so both the cosine and the sine functions, are by themselves solutions to the equation. Okay, so we've seen that, and we've actually, I think we went through differentiating it, and I hope that you were convinced of that. And now we can, for simplicity, we can focus on the simple version, which is just the real or just the imaginary. For example, x equals a cosine, and that's what I'm going to do from now on. In a minute, I'll ask you what I lose by that. Maybe you'll be able to work it out. But this is a bit of a sacrifice, but it makes life easier. I'm just going to look at the real part. So I know that I'm only looking at half of the solutions, but that's fine because it works anyway, okay? And what is this A? By the way, do you remember what A means physically? Yeah, amplitude is indeed the name we give it. But if I think about the displacement of the mass on the spring, does it have any physical meaning? Or at what time does it have a very simple role? if I look at t equals 0, what happens to the cosine at t equals 0? Cosine becomes 1, therefore x becomes a, okay? So this a, which as you said correctly is the amplitude, a, which is also the amplitude, in this case, of this particular solution, it's also x at t equals 0, okay? So it means that this is a particular case that I'm looking at where at time equals 0, the spring has been stretched by a, and now I start releasing it and time starts, okay? If I would have thought about time differently, I would have thought that then I would need not the cosine, but I need a sine, or I need something in between. Okay, that's why it's a bit restricted. This, by choosing a cosine, I'm saying that at time equals 0, the mass was definitely at A. It wasn't halfway through, it wasn't anywhere else, okay? So I don't think that troubles you, but that's something to remember, okay? And so let's try to draw that. I think we did at the end of the lesson last time. We tried to draw, or maybe we didn't draw, but we'll do it now. We're going to draw the solution, the simple solution. When I say simple, I mean this, just the cosine part. Okay, I'm going to draw the cosine as function of t for this particular case, and we've done a few of those lately, so we should be experts in this. Okay, and what I'm doing is I'm drawing the cosine for this time, and as I said, cosines start with 1 at time equals 0. So in that case, the solution here, so what I'm plotting here is I'm plotting x, which is equal to a cosine square root k over m multiplied by t, and I'm plotting that as function of time. So the initial situation here is that at this point, the mass is stretched. So if I draw below it, the mass we have, the mass at this point is stretched by a distance of a from its natural length, okay? So if the natural length, if this is a wall, and this is the floor or whatever, and this here represents the natural length, then I stretched the spring an additional a at time equals 0, and I release it. What does the spring do? It starts going towards the wall. You can see that there's a few special points here. There's a point where it crosses 0. There's a point when it gets to its minimal value. There's a point where it crosses 0 again, and then it's back to the original value. First of all, what is the period of a cosine? In radians, it's 2 pi, right? And we call this thing period in time, okay? Or we could call this particular time here, we could call it capital T, which is the period. And it's also equal to 1 over f, which is the frequency. Okay, do you remember what I'm talking about? If not, stop me, okay? So we have a particular time, which is a full period, when the mass has returned to its original location, okay? What does it do halfway there? So if I look at the position, t equals half of the period. Where is the spring located according to this drawing? It's been moving, yeah. Closest to the wall at a distance actually of minus a, right? So at this point here, the spring is now much closer to the wall, and it's actually displaced by minus a with respect to this. This is the natural length, the L, okay? So the spring is now compressed towards the wall at minus a. Can it get any closer than that? According to cosine, which is always restricted between a and minus a, the answer is no, right? And why is that? Because it started with a certain stretch and it can only compress for so much. And that is the equivalent of the stretch in compression, okay? So it went from a to minus a. And on its way back, it's gonna make it all the way to the original stretch. What are these points in the middle here, where the displacement is zero? These points here, they are quarter wavelengths, or 3/4 wavelengths. What's special about these points? What's the force when the spring goes through these points? So these points are when the displacement is equal to what? 0. And displacement equal to 0 means that the spring is exactly at its natural length. It's where it likes, where it's happy. So it's not stretching, it's not compressing, okay? So somehow the mass goes through these points where there's no compression and no stretch, okay? Why does it go through these points and not stop there? Because obviously nothing is pulling it and nothing is pushing it. Why is it not stopping when it's at exactly the natural length? So we have this spring, it likes to be at L. We pulled it away. Now on its way, it went through L. Why has it not stopped there? Because it's so happy that there is no force. Why has it not stopped? Sorry? Yeah, so one way to think about it is energy. What are we going to do with all this kinetic energy that we've acquired when we were moving, right? Something's got to take it, okay? So that's one way of thinking about it. Another way of thinking about it, I think this is sometimes called the first law of motion of Newton, which means that if you want to stop something, that also requires a force. Okay, it's actually the same thing like the second law, just worded a bit differently. Okay, the things if you throw a hammer out of space, don't try that. Okay, but if you throw a hammer, it will never stop. It will never stop because there is no drag, no friction, no one to stop it. Okay. So you need some force to stop things. So basically the mass is able to go through this point where in theory it has no forces, but it goes through. Let's look at it at something which will make this a bit clearer. Let's look at the velocity of the mass. So this is x dot. X dot is the velocity of the mass. Okay? What is the expression for x dot given the initial expression for x that I wrote earlier, which is this guy? How do I go from x to x dot? What's the dot represent? Differentiation, okay? So one dot means one differentiation. So how do I differentiate cosines? Well, I think we talked about that. What happens to a cosine when we differentiate it? Minus sign. Is something else happening? There's an argument here. So there's the square root k over m has to come out, right? So basically this x dot, which is the differentiation of x, is going to be minus square root k over m multiplied by a multiplied by the sign that I had. If someone does not understand what I did, please stop me, okay? I'm going on because I assume that you understand and I don't want to bore you more than necessarily, at least. Okay, so this is the expression for x dot, unless there are any other thoughts about that. Okay, so this is the expression for x dot. We can also plot it. Okay, I will try to plot it on a separate graph. So if I have here, I'm going to plot, so it's the same thing, I'm plotting time, and this time I'm plotting, so the same horizontal axis, sorry, but this time I'm plotting the velocity. So what is sine of 0? Does someone remember what sine of 0 is? Zero, exactly. So we start at 0. Now what does sine usually do when you go away from 0? It starts increasing because it's kind of chasing cosine, but it has a lag of 90 degrees, okay? But this is minus sine. So instead of going up, it's going down. Okay, so I'm just trying to plot the sine now, it's going down. Then like any good oscillatory function goes up again and then back to 0. So this is the period. This point here is the same time t equals capital T, which is 1 over f. We also have expressions for these frequencies that we derive. Okay? So it starts at 0. It starts at 0 because that's what we chose the problem to be. We chose the problem to be a mass which we take a distance a away from its natural length and we release it. But at time equals 0, it didn't manage to move yet. So it's okay that the velocity is 0. It makes sense, okay? Why is the velocity negative? Well, it's negative because it's moving against the direction that I displaced it. If I pull the mass, if a was positive, the velocity is in the other direction. So it makes sense it's negative as well, okay? What is the minimal value that this function will reach? We have to look at the mass here. So if I look at this expression here, what is the most negative value that I could get from this expression, from this square root k over m multiplied by a multiplied by sine. Remember that sine and cosine always can only go from -1 to 1. They can't do anything more fancy than that, okay? So the largest thing that the sine can be is 1, but if it's minus sine, it's going to be -1. And then if it's multiplied by square root k over m, a, that's what we're going to have, okay? So this value here must be minus square root k over m a, okay? And the positive one is, of course, plus square root k over m a. This is the value here, okay? And we can see some interesting things. At what time do I have either the highest negative velocity, if you want, or the largest negative velocity, or the largest positive? At what points in the period is the mass moving the fastest? And the answer is, it's not at half. It's not halfway. It's not at t half. It is at t quarter and t 3/4, either negative or positive. Does that make sense? In fact, it does, because this is the moment that the mass is going through the natural length of the spring. So these are the same points that the displacement was 0. So the mass goes through these sweet spots where basically there is no force, but it is accelerated as much as it could. It has the fastest motion, and from now it's going to start decelerating. Okay, and then vice versa. It's accelerating the other direction, and then it's going to start decelerating after that. Okay, so that's why the velocity gets its maximum at these points. Any questions about that? Yes, no, maybe? Nothing. Okay. Now, just to, again, tie up with what we did in the previous lesson, let's remind ourselves that we actually know what the frequency is. Now, we can either look up the notes that you've written, or we could maybe remember, or we could work it out. What expressions do we know about the frequency, the angular frequency, and the period of this very simple system? You remember that we could write cosines as cosine omega t. I don't know if you remember, you don't remember, but that was something I showed you last time, that a cosine can be written as cosine omega t, where omega is the angular frequency. So what does omega look like in this expression? It looks like square root k over m, okay? Again, I'm writing it because it's something we did last lesson. I'm doing it a bit quickly, but again, you can stop me if it's unclear, okay? So basically this omega is equal to square root k over m. I can identify that from its position in the cosine. What's the relation between frequency and angular frequency? 2 pi, okay? So that means that the frequency, which is omega divided by 2 pi, is equal to 1 over 2 pi square root k over m. And finally, what's the expression for the period? Well, the period is 1 over f, and I just wrote f, so all I have to do is to invert this somehow, and this is going to be equal to 2 pi multiplied by square root m over k. Note that inside the square root, I've inverted the fraction, okay, because it's 1 over. So I've inverted 2 pi, I've inverted the fraction. Okay? Okay, I suddenly remember it. Yep. I suddenly remember that you guys actually want to learn chemistry. So let's do a chemistry example, okay? So in this example, let's take some kind of a surface. That would be some kind of a solid surface. Let's say copper, nickel, whatever, okay? Some metal, piece of metal surface, okay? Now I take an atom. Let's take, for example, a sodium atom. Okay, so if I take a sodium atom, and this is an atom which is in the gas phase, somewhere above this solid, okay? And it's moving in the direction of the solid. As chemists, what would you think would happen to that atom when it reaches the surface? And maybe there's more than one answer to that question. So there's a sodium atom reaching a copper surface. Come on, take an educated guess. Worst case, you're wrong. You're probably right because lots of things can happen. So the chance of you getting it wrong are actually quite small. Pretty much everything can happen, okay? Come on, give me one scenario. Bounces. So one scenario is a sodium atom comes in and plays squash, okay? Comes flying out after hitting the surface, maybe elastically, which means with the same energy, maybe inelastically, and so on. Now, with this would actually be a very good likelihood for a helium atom. Helium atom comes in, sees the surface, you know, he's so full of himself, sitting with all the noble gases, okay? And he doesn't care about the surface and he bounces back, okay? But a sodium is, you know, is a pretty reactive atom. So what else might happen? It's true, it might bounce, but there's another event which could happen. It could stick, right? It could form a chemical bond. So if the atom doesn't bounce, but actually stays on the surface, so we have this other sodium here, which is on the surface, what would you think is the distance of this atom from the surface? Is it sitting on top of the surface with this displacement of 0 from the ions of the copper or whatever? Is it far away? Is it in between? What do you think? Again, just intuition. I know you haven't learned this specific question. What's your intuition on that? Okay, you're giving an outreach to children, okay? They have no clue. Whatever you say is right. You just have to say it with confidence. So what's going to happen to this atom? Very, very close. But 0? Not quite 0, okay? So there's going to be some kind of a distance here, thank you, which will be, I don't know, whatever. Let's call this x, okay? And this would be the bond length. So sodium is now forming a bond with the surface. It will depend actually on the interaction between the electrons of the sodium and the electrons of the copper and the ions, and it's bloody complicated, okay? But there will be some distance, which is usually what we call the minimal energy distance. So this is the favorite sweet spot of this atom close to the surface, and it's not 0. It will typically be on the order of, I don't know, let's say, whatever, some kind of 2 angstroms, okay? So that's 2 times 10 to the minus 10 meters. It will actually not matter at all, as you will see soon, okay? This distance. Now, what does the atom do there when it's there? Is it sitting absolutely still, you know, freezing for a photograph? What is it doing? I'll give you a hint. The surface is at room temperature. What does it mean, being at a temperature? It means that it's moving all the time. Okay, temperature is random motion. I don't know if you've learned that already, but you should have, okay? And if not, you will. So having a temperature means you have random, what's temperature? Except for the fact that we have to stay in a room and isolate. Temperature is the fact that you have random motion. If anything which is not 0 Kelvin is moving, it might look still, but it's actually full of motion. So this atom is actually not staying at all. It's vibrating up and down, or left and right, or whatever it wants, around that equilibrium position. So let's try to solve that. And we could say, well, we haven't learned anything about sodium atoms, we know nothing. How can we solve this? And the answer is, yeah, well, we know about springs, because I've bored you about springs for about 2 lessons now, right? So you're experts in springs. So let's just treat this bond as if it's a spring, okay? We'll see later it's actually not such a bad assumption, okay? So what we're going to do is we're going to basically assume that this chemical bond is going to be like an ideal spring, and we're going to give it a spring constant, this k, which is this F equals minus kx. We could give a value to this k. Let's say, for example, this would be 1.51 Newton meters, okay? So it's Newton divided by meters. That makes sense because if I multiply k by x, my meters, I have to end up with a force, and forces are newtons, okay? And I try to use MKS always, just to use one set of units, okay? Unless it's an exam and I want to get you guys all confused, and maybe I'll put in something else, okay? But generally for myself, I make life easy and I just try to stay with MKS units, okay? So it's Newton per meter. And we also can, well, to solve this guy, we're going to need to know what the mass of the sodium atom is. So it is, I believe, 3.82 times 10 to the minus 26 kilograms. Now, in this course, when we do these type of calculations, a more serious remark about units is that I tend to stick to the mass of the individual atom rather than the mass of the mole. And I tend to stick to the energy of an individual atom or a molecule rather than the energy per mole. It is possible to convert, but there's no point because everything we're saying is true for an individual molecule, okay? We're looking at individual molecules or individual atoms. So that's why it makes sense to talk about the mass, not in AMU, but the actual mass in kilograms of an individual atom, okay? So basically, what do we know? I mean, we could ask lots of questions here, but for example, we could ask ourselves, what is the period of oscillation? Okay, this is this capital T. But if we use an ideal spring, then we actually know the answer for that. Okay? Because the angular frequency is square root k over m, the frequency is just 1 over 2 pi that, and the period is 1 over that. Okay? So we actually have the expression for the period written here. So that could, in theory, save some time, but I will rewrite it. And so that's T equals 2 pi square root m over k. And we could actually work out what that is, or try to. And if you put in these numbers, and you can try it at home, if you're trying to do your exercise and you're not sure you're doing it correctly, you could try this example. And the result I got was very, very close to 1 times 10 to the minus 10 seconds. Okay? So that is the time, so it's 10 to the minus 10 seconds. 10 to the minus 6 is 1 over a million. 10 to the minus 9 is 1 over a billion, so it's 1 over 10 to the 9, okay? And that is 1/10 of that. It's pretty small time, pretty short time. But this is the time it will take this atom to go back to its original position, whatever it is. Note that this particular question, note that this is not a function of initial displacement. So this A that appears in the solution does not, that appears in the general solution is not needed for working out the frequency. It's a rather peculiar property of ideal springs. It means that if I take this sodium atom, it's very hard to do it, it's very small, and I plug it, and I'll answer your question in a second. If I move it from its favorite place a little bit, or I move it double that, it's going to oscillate at exactly the same frequency with the same period. Yeah, sorry, was there a question? You got a different answer? Already. Okay, what did you put in for a mass? 3.82 let me just check. The chance, first of all, the chance of me doing a mistake is very high, but again, this is, did you not get just something 0.99 or something very close to that?
This minus 15, I got times 10 to the minus 30.
Okay, let's go, that is, I think it should not happen.
Yeah, what's that number there? Where it says k is equal to something times n over n, what's that?
Sorry, okay, so this is, k is the spring, so first of all, I'll check my numbers in a minute, okay? I just do things one by one. But this is, an ideal spring has a force which is equal to minus kx.
I understand.
Just what I wrote.
What is that? Yeah, what does it say?
So it's 1.51, that's just a number, newtons per meter, which means if you multiply this by a distance, you'll get that answer.
I understand. What does it actually say?
Oh, with the numbers. Sorry, that's my handwriting.
Yeah.
Okay. Okay, just say, your handwriting's awful. Could you please tell me what's written there, okay? I'll get it faster. But yeah, I do think that the result is actually right, but I will double check myself, okay, if you want. Sorry, you are right and I'm wrong, okay. Thank you, okay. I mean, it's not a great idea to actually, while I'm talking, do the exercise because you might miss my next point, but in this case, it was an excellent idea because you found a typo, which is actually that I forgot to 10 to the -4 here. Newton per meter, okay? It's actually, I do these mistakes on purpose just to see that you're actually listening. No, seriously, I do these mistakes all the time, so it's very good you caught that one, okay? So sorry about that. So I gave you the wrong number. Now that makes sense because, yeah, it should make sense, okay? And again, we can check the numbers later and see that I haven't made any more mistakes, but I think I haven't, okay? Let's see if that's actually, yeah, that should be okay. Okay, so let's continue and ask another question about the same sodium atom. But does everybody understand? Sorry for the detour with my typo, but does everybody understand the way I solved this question? Okay, because you're gonna have to answer it as well. Okay, and you're gonna have to get it right. Unlike me, you know, I lose a point. No, so what? But then again, you have to get it right, okay? But the main thing is to understand how to actually do this thing seriously, and if not, let me know. What other question could I ask myself? Well, I could ask myself, what is the velocity? Maybe I'll move to the other board. I could ask myself, what is the velocity of the sodium atom when it's exactly at its natural distance from the surface, okay? Or you could say, what is the velocity? What is the maximal velocity of this Na atom as it moves oscillating? And the maximum value, either negative or positive, will be when it passes that point, right? What do I mean by that point? The point where the displacement is 0. So when it's just passing this sweet spot, and on the other hand, the velocity is at its maximum. What we wrote previously, the graph that I just erased, which was for the velocity, oscillated between what values? It was minus a square root k over m to plus a square root k over m, right? So we know that this velocity max is equal to square root k over m multiplied by a. Okay? Does that make sense? So what is a? Now, basically, we see that this requires an initial displacement value. So what do we learn from that? We learned that when we take this atom, and let's say we move it a little bit off its natural length, natural bond length, it will oscillate at the same frequency regardless of how much we moved it by. But the velocity as it passes is going to be larger the more we pull it initially, because that's this A here. If we pull it 5 angstroms away from the surface, it's going to have a very high velocity when it goes through that maximum. If we pull it just 0.1 of an angstrom, it's going to have less, okay? So for example, just again, if you want to put later numerical values, for example, and hopefully this time they're actually right. And for example, for A equals 0.2 times 10 to the minus 10 meters, that would be like a reasonable value for oscillation. What I got was a velocity which was something, okay? I think it was 1.26 meters per second. That was what I got. Again, it could be wrong, but I think that's right, okay? We could also ask you, and when I say we could, it means we will actually, we could also ask you, what is the maximum kinetic energy that this sodium atom can have? okay? But kinetic energy is simply half mv squared. So all I could do is I could take the highest value for this x dot for v and plug it into the equation, okay? Again, you can do the calculation. What I got here was that for this example, with this displacement, I got that as 3.02 times 10 to the minus 26 joule. Now note that this is also a function of A, okay? Like the velocity, because the velocity is a function of A, therefore also the kinetic energy is a function of A. And actually, if I write that down, that's more interesting. If I write that down using the equation, and I always suggest that when you do your homework, you do that before you put in the numbers. So you write down the actual expressions. What you're going to get is you have half m multiplied by this guy here, which is square root k over m a square. What happens to a square root when we square it? We're back to what's inside, okay? So we have, as a final result here, we have half, let's do it slowly, half m k over m a square, but the m and the m cancel out, so we have half k a squared. Okay? So when you're asked in an exam or even in a workshop exercise to calculate the kinetic energy, write down the expression as much as you can in full, and only at the end put in the numerical values. Because then if you do a silly mistake like I did, which is forget some power, I'm going to be very generous with that. But it shows that you understand, okay? I don't really care about the type of mistakes that I could do myself. Quite often. Okay, so now, if this is clear, I want to talk about an additional important point now, which is, could we do it differently? And I think one of you suggested it. Basically, could we approach this the question with the conservation of energy? And obviously depends what exactly you're asking, but at least some of these questions you could. Okay, similarly to what we had when we were playing with gravity and stuff. Okay, so what are the types of energies that we have here? Let's start with the obvious one. When the mass or the sodium atom is moving past its favorite position, this is the position where there is no force, what type of energy does it have? It only has one type of energy. As it's passing through this point where there is no force, what kind of energy are you left with? Because it's moving. So you have kinetic energy, okay? So when the sodium, just have to replace that one slide. At the point, and it's awful, sorry. These guys die before they start living. At the point x equals 0, okay? This is the point of the natural length of the spring or the bond. There is no force, okay? Only energy we have is the kinetic energy, which we just calculated, which was half mv squared, or the value that what we got was half times a k a squared, I think, right? If we write it differently. Is that right? Yeah. What is the kinetic? Yeah, sorry, but I cannot see what it says now. Oh, sorry about that. Yeah, this is really a horrible. Okay, let me so I'll read it out now and then I'll try to move to another board. But what's written here is that at the point x equals 0, which is where you have the natural length, then we don't have any forces, and the only energy we have is kinetic energy. That kinetic energy is half mv squared, or as I wrote it earlier, it's also this expression, half k a squared. Okay? You got a pen, which is better than my pens. Let's see.
It's just black.
That is good. Good start. Thank you very much for that. Is that better, by the way? Much better. Okay. Okay. There goes the green. Not touching that again. Thank you. Okay. So, what type of energy do we have at the very start? At the very start, we said the sodium was starting at a distance a away, and we're just kind of leaving it go. Okay. So it still hasn't moved. The velocity is 0. So what energy do we have? It's a type of energy we talked 2 lessons ago. Elastic energy or potential energy. Okay, so that's potential energy. What is it, potential energy? This is the potential to perform work. Again, this might sound like 2 lessons ago, but that was not that long ago. So basically, we have at time equals 0, we have only potential energy. We have no kinetic energy because we have a velocity of 0. Okay? What is the equation for potential energy? So the equation for potential energy was minus an integral of the force. I'm going to write this without vectors because life is difficult enough. Okay, so I'm just going to write this in 1-dimensional. So just f dx. Okay? And it was from some kind of reference to the value of x. This might not look familiar because it was 2 lessons ago, not 1 lesson ago, but you have seen it because I know the teacher which wrote that on the board. Okay, so basically, what's written here is an integral of f dx. But what is the f for the case of a simple spring? What's the force? What's the relevant force? It's not mg this time. What is the relevant force for a spring? It's always ma, but it's also minus kx for this specific case. Okay, it's ma, that's always, right? But if we want to write it in terms of x, we have to look at the specific force. This is a spring, and if you displace it by x, you get a force which is minus kx. So if I write this guy here, we have an integral of minus kx dx from this reference point to x, and everything is minus again. Usually we take, for the x reference, we usually take 0. And again, this is something I talked about. Might have been hard to follow the first lesson and the second lesson or whatever. What I get here is essentially k, because the minus and the minus are canceling themselves out. And here I have x dx. What's the integral over x when you integrate over x? So it's like integrating in time over t. It's just x and t, doesn't matter. These are just names, okay? So instead of t, it's x. And I'm integrating over x. So x becomes x squared over 2, okay? So basically what I have here is half k x squared. Okay, that's actually a very important result. So I'll write it on the other board as well. It is. Okay, so the result we got was that we have a potential which is equal to half k x squared, where x is the displacement of the mass on the spring or the molecule on the bond or whatever, okay? K is the coefficient of the spring or the strength of this chemical bond, and this is U. If our initial displacement was A, what was the potential energy at this position? All we have to do is insert A instead of X. Okay? So for example, for the question, so this is a general thing, but for the question we looked at, for the question we solved, initial displacement was A. So this means that the potential energy was half Ka squared. Okay? So that was for the initial question we solved, the initial displacement, sorry, that is really awful, was A, right? That's what this A cosine square root of K over MT means. What was our result for the kinetic energy at the maximum? When we wrote the expression for the kinetic energy, what was it? Well, I very much hope it was exactly what we got now. So I very much hope, and you could look in your, I've erased my board, but I very much hope that what I wrote earlier was half Ka squared. Why am I hoping that? Because whatever we have in the potential energy, if it hasn't become kinetic energy at the point where there is no force, then something's wrong with our calculation. And this is the idea of conservation of energy. You can't lose energy, you can just convert it. Okay? Is that okay? Any questions up to now? None? Okay, so this guy has a name. Okay, so this is called also the harmonic potential. So harmonic potential is a general, it's a more general name for a potential which looks like x squared. It has something multiplied by x squared, okay? And basically a harmonic force is this F equals minus Kx. It's true that so far we talked in terms of springs, but what I'm saying now is that this potential and this force are really important in chemistry and in physics, and they have a general name. And that general name is harmonic potential. And you could find various circumstances where this is a good approximation for the potential and for the force. And this means that the solution that we found, the solution of an oscillating cosine or sine, is a solution for many, many problems. It's a solution for any problem which has a potential which looks like that. So if K is not the spring constant, but it's something completely different, that's okay. It has the same mathematical function. It's going to have the same result. Is that point clear? Okay. So a few final remarks, because I know we're a bit short on time. A few final remarks which are going to be helpful for the videos of next week. Okay. So first of all, I want to make a point here. You remember that I chose, when I was talking about the spring, I chose to describe the position when the spring has no force. I chose to call that x equals 0. Okay? I could have chosen something else. So I want to just note that there's an alternative a way of writing this harmonic potential and the harmonic force and this is that the potential can be written as minus k x minus x naught square, and the force, sorry, without the minus, and the force can be written as minus k x minus x naught. So again, the potential energy as k x minus x naught squared, and the force as minus k x minus x naught. It's very similar to what I've written above. The only difference is that now x is actually the position, not the displacement. X is the position, and x naught is what's sometimes called the equilibrium position. So this is the position where there is no force on the particle. It's not pulled inwards, it's not pushed outwards. Okay? It's a very simple conversion from one set of equations to another. It's just that the meaning of x has changed slightly. Before x was just a displacement, and now x becomes the actual. So in the example that I had for the sodium atom, you remember I said, let's say the natural bond length is 5 angstrom. So x naught would be 5, and x would be whatever that number is. If it's higher than 5, it would be 6. If it's lower, it would be 4, and so on. Okay? So what we're going to do, so the next video you're going to watch for the next lecture is kind of, we're switching gears. So maybe if in the first week we were in gear 1 and now we're in gear 2, maybe. Okay? This video represents a shift in gear in the sense that it is advanced maths. Okay? So what you're going to be learning about is something called the Taylor series. And some of you, at least in the past, some students have said, but this is not even A-level math. This is more than A-level math. And the answer is yes, you're correct. It is more than what's learned in A-level math. It's advanced math, but you need to know it as chemists. And that's the nice thing is that I'm not going to assume that you have A-level math. So I'm going to, in this video, I'm going to take you through it. And all you need to know is differentiation. You don't need to know anything more than that. So don't get freaked out. And if there are questions again, it will eventually, it will stand still eventually. So don't get freaked out if it looks complicated. What it is, it's basically what we're going to do is we're going to find a way of taking this potential here, which you guys have worked hard on understanding, hopefully understanding the solution to, and making it applicable to all kinds of other situations. Ideally, and this is true, each time we have a solution for something, we try to look at every problem as if it's somehow related to the thing we have a solution for, okay? It's like looking for your keys wherever you have the light, not necessarily where they fell, okay? So that's what we do, and we want to basically take this harmonic potential and make it work for lots and lots of functions. And this is what the Taylor series is going to do. And I know I said this was the last thing, but just one question. In the video, the only other term I use except for differentials is factorial. Do you know what factorial is? Do some of you not know what factorial is? Okay, yeah, factorial. So if those which want me to remind them, instead of reminding themselves, factorial is just it's a shorthand writing, okay? Like a lot of these things are. So if we have 5 factorial, and that's supposed to be a 5, that is equal to 1 times 2 times 3 times 4 times 5, okay? 3 factorial will be 1 times 2 times 3. These are all pretty, okay, this is just a way of writing it. 1 factorial is 1. And does someone know what 0 factorial is?
1.
Exactly, 0 factorial is 1. And that's not because it makes sense. It's just because someone decided it is, okay? So 0 factorial is defined as 1. It's like a power of 0, okay? So I think you now have the tools to understand this lecture. If you don't, let me know, and have a nice weekend.